acres that's located out in Woodinville, Washington. Anyone heard of us or been out there yet? Yes, one? Great, thank you for coming out. Have the projects been introduced at all yet?
Not yet, just a little bit.
Just a little bit?
Yeah, I
Okay.
think I may have flashed the projects on the over. I haven't passed them out yet.
Okay.
But I do have
All
them
right.
with me today.
Okay, those are great summaries. I love how concise they are. So, maybe
You
I
want
can-
to pass them out?
Sure, yeah, okay. So 21 acres is a LEED Platinum certified building and 12,000 square foot building. We are literally on 21 acres, so we also have and support regenerative farming practices. We have wetlands and goats and sometimes chickens. So our mission is all about sustainable living, green building, and regenerative ag. So, anyone familiar with LEED certification? A little bit, yeah. It stands for Leadership in Energy and Environmental Design. It's a program from the U.S. Green Building Council. And LEED Platinum, which is the status that we have, is the highest level that you can achieve. And some of these, you'll see, well, I'll talk a little bit about our systems. We care greatly about climate change. That's our mission, is to solve climate challenges. And so everything is geared toward energy savings, energy efficiency, low carbon emissions. And so we have some really cutting edge and innovative processes at our facility that I'll talk about. A little bit about my background. I have a degree in undergrad in environmental science and a master's in environmental engineering. But that fell under the civil engineering category, so I'm not a mechanical engineer. And my career was spent doing remediation, so I was doing a lot of cleaning up of contaminated soil and groundwater. So I just got into sustainability and green building about 3 years ago. So I'm actually a little bit green in this area. I do have my LEED accredited professional credentials, but I'm also kind of like feeling my way through some of this stuff as well. So, and Earth Day is coming up. So we are really busy right now preparing for Earth Day. And if anyone wants to come out to campus to volunteer, that would be lovely on Saturday. Okay, great. Do I have this is my mouse? Oh, is it really fast? Oh, it's fast, okay. Okay. So, just to orient you a little bit, the campus and our building. This is just part of a bigger presentation I did. So this, here's an overview that I like to show of our building. This is the 12,000 square foot building that we have. And this just points out some of the ways that we achieved our LEED certification. And so we have stormwater treatment. We had a living roof that we just had to take down. We treat all of our stormwater on site with rainwater or rain gardens, and then it's surrounded by bioswale. We do all of our on-site wastewater treatment, gray water and black water. We have our solar panels and car charge. I mean, like we literally have everything. We have composting toilets. But we'll talk a little bit more now about the mechanical systems that we have. But I just kind of want to give you a setting for 21 acres and what we care about and why we're doing the projects that we're doing. So let's see.
So Kelly, you said that the building is LEED
Platinum.
Platinum, and what does that exactly does that mean?
So, well, actually, then I will show you this first slide. That will. So, back when the building was constructed, this is called LEED Building Design and Construction for new construction. We achieved the platinum status in 2013, and at that time, the rating system they always have a checklist, but this is what the checklist looked back like in 2013. So it has all these different categories, and this is how we earned our points. So there's sustainable sites, materials and resources, indoor air quality, water efficiency, energy and atmosphere, and then this is kind of a strange category, innovation. So wherever you see, like this means that we earned 1 point out of a possible 1 point. So there's some zeros, we just didn't get points for a few things. And the U.S. Green Building Council weights the categories by what they think is the most important, and climate change and carbon emissions and energy efficiency is the most important to U.S. Green Building Council. So you can see that this category gets a total of 17 points possible, whereas they might think water efficiency is a little bit less important in terms of sustainable goals. So the total amount available is only 5 in water. And so at this time, to be LEED Platinum, you needed 50 points. We earned 54. So at the time there was, you could just be certified, or you could get silver, gold, or platinum. So the whole rating system has changed. Now you need 80 points to get platinum. They've kind of moved things around, and they make that goal harder and harder and harder. As things become more sustainable and green building becomes more common, they push that goal post a little bit further. So it's a little bit harder to get platinum. So we're currently, I just submitted a year's worth of our energy and water data, transportation data, indoor air quality data, and we're gonna get what's called an O&M, or Operation and Maintenance certification. So I'm currently trying to get LEED Platinum O&M certification to show that our building is still a high-performing building. So, does that help answer?
So you use the expression high performance building, which is another, you hear all these terms, green building, high performance building, net zero, negative, what's the past net zero is negative?
Oh, if you actually become like a, I don't know, carbon sink or something, like, yeah, if you're producing more renewables than you use.
So is 21 acres net zero?
We are not net zero. So we're generating electricity with our solar panels that you saw. That's a 25 kW array. And that produces about 20% of our energy use that we use in a given year. So we, because we support local farms, and we have a market and a commercial kitchen, so we have a lot of refrigeration. So our refrigeration uses up a decent amount of our energy needs. So we did just have to take off the living roof, so we are going to install more solar panels, so that that'll get us closer. But I don't think that we'll ever be net zero. So I'm currently designing my own home, and I'm hoping to get a net zero certification for my house. So yeah. Is that any questions about LEED or sustainable? Yeah.
Can I ask why you had to remove the living room?
Why did we remove it? Yeah, let me tell you. So that that's kind of an engineering question, because let's see, trying to do it quickly. So the living roof was comprised of what was called cell tech. So that it was these plastic cellular things that, like, they would start out this way, and you'd expand them, and you would fill those with the substrate and the plants. And the cell tech had like cabling that was attached to, like, bolted to the actual roof structure. And when I look back, because I had to try to figure out why it was failing. So basically, the cabling for that cell tech was put on 5-foot centers, and it should have been put on 2-foot centers. And so in between all those cables, it just started sliding down. So you could see the actual material going like this. And we weren't sure at what point it was going to actually have a failure and slide all the way off. So we looked at, I tried to see if we could fix it, and everyone said no. You'd have to replace it entirely. So rather than replacing it with a new living roof, we're going to go for solar panels. So try to get that renewable energy up for us. Yeah. Anything else? So let me see. On your sheet that I handed out, we have 3 projects that we came up with. So this is what I felt like I might be able to help assist with throughout this quarter. And the first one is about our domestic hot water. So we currently have what's called ground source heat pumps for our building heat and our domestic hot water. Are you guys familiar with heat pumps? I don't know where you're at. Yes? Okay, and ground source heat pumps means that we have 3,000 feet of coils that are buried beneath the ground that are capturing that heat from the ground and transferring it into our system, and then we have the 1010 heat pumps that do our building heat that transfer it into our radiant floor heating that we have that's going throughout the building. And then that same ground loop also goes through a 510 heat pump heat exchanger that does our domestic hot water. So the first problem that we're having, well, the 510 heat pump is 10 or 11 years old at this point. At that time, those heat pumps couldn't get the water up to temp. It couldn't get up to, it needs to be up to 140 degrees for our kitchen, and it wasn't able to do that. So a decision was made back in the day to install a natural gas backup hot water heater. And so we currently use both systems for our domestic hot water. And as we try to decarbonize the building and get to net zero emissions, carbon emissions for the building, we want to get rid of that domestic natural gas backup hot water heater. So the first project is to help evaluate, well, we have 3 different ideas. I think they list them all here. Yeah. Well, it's to look at the system and then help come up with the best solution. We already have an idea for three different ideas. One would be to replace the current 510 heat pump with a new unit that's capable of achieving those temperatures, and then we can just take the domestic or the natural gas heater out of the line. The second solution is to leave the 510, the older 510 heat pump in place, but add in a newer, smaller air to water heat pump that would then get that water up to the temperatures that we need. And then the third option is, well, I would love to do, because the other thing about 21 acres is we're a demonstration facility. We have tours and we bring people through and we're trying to be innovative. And I love the idea of a solar hot water collector. So that would be a great visual project for when guests come to tour the building. And so the third idea is to do a domestic or a solar hot water collector system that would still probably need one more ancillary technology to get that temperature up to 140 degrees, and then keep the 510 heat pump in place. Any questions about that? No? So then the second project on here is to do a process and instrumentation diagram for these systems. And these 2 projects kind of feed together, and so I'm not sure how that would work with, but I think both groups could be working together collaboratively, because you kind of need the PNID in order to try to figure out the ways that we can upgrade our domestic hot water system. But we have noticed that when the 510 heat pump that's doing the domestic hot water would go down, we had our building heat go down. So we lost heat in the building, which didn't make sense with how I thought the system was plumbed. And so I've been wanting to do this PNID for a long time to try to understand how these 2 systems are relating. Because all I know is that they have they share the same ground loop. So my understanding was that maybe when the 510 heat pump went down, the load demand for the 1010 was too great, and it needed the 510. But I don't understand why it would do that, why the whole building heat would go down. So that's a solution I would love to try to figure out. So that's the second project, is the PNID for the system. And the third project is something entirely different. So any questions right now about the way the building's heated or domestic hot water? Okay.
Yeah, the PNID, I don't know, are you familiar or have you heard of that term PNID? It is, for process engineering, it's usually a starting point for engineering design. It's the whole system overview, and it shows all of the piping, how everything is connected, the pumps, the valves, and then it shows where the instruments are, and where the instruments, go through and what the instruments are, what they're measuring, and then it has electrical connections or instrument air connections between the instruments, like the sensors and controllers. So someone can look at this diagram and see, oh, here's the water, it's coming from the ground and it's going through these pipes and going through this pump, and there's a valve here, and that valve is just a manual on-off, and here's a valve over here that's a control valve, and that valve is being controlled based on flow rate. There's a sensor monitoring the flow rate, And it's skill set, especially if you're going into consulting or work where you're designing large-scale commercial HVAC systems, because it involves thinking about the process, big picture, and putting it on there, visualizing it and laying it out on paper. But in some cases, usually we do this at the start, and then we file it away, we store it, so you can always go back to it. But sometimes, especially with old legacy systems, either the P&I doesn't exist, or it's the systems are modified so much the P&ID isn't current, so you have to go through and redo it. So this is a chance to go and actually, to do a P&ID from a built system, you literally have to walk it. You walk the system all the way around, you look at everything that's there, and you ask, what does this do? Why is it here? What does it do? How's it wired up? And you just make drawings and make notes, and it's a great way to learn how something works.
And super helpful for like a facility manager, for the operator in the future.
Yeah, absolutely.
Yeah, because the first thing when I get to 21 acres, I'm like, okay, well, where's the drawing? How is this all wired? Where's this all connected? And I don't have that. So I have this really old manual that I actually had to dig through our old files to find, and it's not right. So yeah, this is a super basic. I can't get it to rotate without updating because I'm just in Reader right now. But this, this is a piping layout. So, super kind of basic process flow diagram or P&ID of, it covers this. I have a few things. I'm not sure how, where we'll start. I have a few hand sketches and a few manuals and stuff like that that would at least maybe get the ball rolling. I've been just trying to update this myself. It doesn't show, for example, the backup natural gas heater, and it doesn't show how the ground loop system works tidy. So this is the 10-ton heat pump that does the heating for the building, and the 5-ton that does the domestic hot water for the building. But yeah, I would love to have something that was current and accurate. So it helps with troubleshooting too. Any questions? Okay. So the other project, so again, we support regenerative ag and local farmers and local food systems. So refrigeration for local farmers is super important, and one of the things that they are struggling with. So one of the things that we offer for the Sammamish Valley farming community is refrigeration. So it's called a food hub. So we have a post-harvest refrigeration unit, or a FRU, P-H-R-U, FRU. And the farmers can bring their produce and products to our FRU, and then they get distributed from there. So whether they're going to retirement communities or schools or nonprofit food banks, they need that place as like a central hub for that food to then get distributed. And then we also, of course, have our own market at 21 acres that requires refrigeration. And then our commercial kitchen is about to be taken over by a really big operation. So refrigeration is becoming critical at work, and we're out of space. So our FRU, I only have, let me see this one. Let's try a different one. Oops. Okay. So the FRU was originally designed to achieve a different type of certification called the Living Building Challenge. And so it was designed to be completely off-grid. It was going to have solar panels and a living roof and rainwater catchment systems and all sorts of stuff. That all kind of went away. It is still incredibly highly energy efficient. It's constructed with SIPS panels, or structurally insulated panels. And so it's it's cooled with just a heat pump, just a traditional small heat pump it uses a cool bot to like trick it so that it gets it down to the proper temperature for produce. And so this FRU, which it's about 10 by 10 or 10 by 8, a walk-in cooler uses the same amount of electricity as a standard like residential refrigerator, and we get a walk-in cooler with that. So we're out of space. We would like to either expand the FRU and make it bigger, or do a second similar structure nearby. It does not need to be off-grid, but it does need to be energy efficient. And, you know, we're not gonna go for a certification, so it doesn't have to have living roofs and rainwater collection and stuff like that. It's a little more functional for the building. The building itself, again, is gonna get more solar panels, so that's kind of our goal, is the next refrigeration unit can be on the grid, and then we'll be using solar panels on the building to try to get as much renewable energy for the project as we can. So a lot of the, you know, I have a lot of the original design concepts. So originally it was gonna have two, so you see there's cold storage here. It's gonna have another staging area here and another phase over here. This is all we have right now. It's just one 8 by 10, 10 by 10 square. The outside of it is also cork, so that the reason it was designed with cork was to be a carbon locking and try to get that net zero for carbon for the building. And then originally it was designed to be movable. So that was a design criteria, was that it could be go on the road if it needed to be moved around, and that is no longer a design criteria. So there's a lot more flexibility than we had at the time, but we do have some of this kind of background on how the original unit was designed.
And that, the SIP, the wall, that's really thick.
Yeah, I think it's 8 and 8.5, 8 and 1/8 here. It varies, I think, depending on which side. This one I think says 5.5.
But do you know the R value of the?
Yeah, so the 8 and 8 is R32,
R32.
and the 5.5 here is R23.
Yeah, those are really cool because you just buy the whole wall. It's already pre-made, so you don't have people. You're not building a wall on the site.
Yeah.
But they are expensive, I understand, compared with.
Yeah, with standard building materials, I'd have to do a cost comparison. My house actually that I'm designing is going to be constructed with SIPs, but I haven't compared it to traditional. I always say, sustainable building costs more in the beginning, but your return on investment in energy savings or water savings, beyond the good that you're doing for the planet, your return, it comes back, I think, in 10 to 15 years, in my opinion.
And what is this standard now for new construction, like for housing? Is it R?
Oh, it depends on your climate. I don't have that all.
R20?
Yeah, it
Something?
depends on what climate zone you're in too, and so.
I still live in the world of R8 to R16, 1960s vintage, but I know they're way up there now.
Yeah. There's I'm super interested in the energy codes that are, the Washington State energy codes, and so I've been doing some webinars and stuff, and so their motto, the WSU motto is build tight and ventilate right. So yeah, the new homes are just super tight, super insulated. So they say that my house, we should be able to like heat it with, just running the refrigerator, because that's going to generate its own heat. So.
Yeah, mine you want ventilation, just stand next to the wall.
Yeah.
Or window, even if it's closed.
Well, and so we're installing actually heat recovery ventilation and energy recovery ventilators. Is anyone familiar?
Well, we talked about that last spot. Yeah.
Okay. Yeah. So that's I always say if you guys want to be cutting edge, like that, that's going to be the next big thing is these ERBs.
Are you doing that now? You're putting in ERB?
What's that?
You're putting in the ERBs?
Mm-hmm, yeah. So if you build these houses this tight, then you really need a good ERB system. Mm-hmm. Yeah. And that's something, I think that was kind of on our list of a project, something we could do at 21 acres, but I just don't have the capacity to take something like that on. So.
Yeah, I need another quarter really to get into those
Yeah.
decent
Mm-hmm.
edge systems.
Any questions? No? Okay. We're good? Is that my little, I can't see. Oh, it's here. Okay. Where's your computer? Where did you plug it in?
Oh, the little USB. South down here.
Right there. Gotcha. Okay. Well, I will head out.
Oh, okay.
Do you have anything else?
Well, I think that's good for now.
Yeah.
We have an exam on Monday, so that's kind of a turning point in the class. So after the exam, we will, I'd like to get the project teams set up by the end of next week. So
Okay.
by Wednesday's class. And, sadly, there's only 3 projects there, so only about half the class will be able to work on these projects. So we'll have to figure out how we're going to allocate teams to the projects and try to get some other options in as well. Hoping to have some here in our own facility. Actually, they may have something that is a sort of a P&ID, tracing a process and documenting what they have. Anyway, so next week, so think about who you want to work with, and then by next Wednesday, we'll have that get that going. And so for the rest of today, today was designed to, not really have new material, but to just look back over what we've done and review for the exam. And I've put together some practice problems that you can do to get ready. And but before I hand those out, last time I handed out the space cooling and heating loads examples. Did anybody get work through those or get any answers?
I only did number 1.
First one?
Yeah.
What did you get? For you?
Yeah, for you.
Okay. Well, I got 0.059.
Yeah, I got that.
So it may be just some slight differences. This is our
0.071 rounding error. Yeah, probably. I mean, probably.
ETU and
Would it be the other way around? Because would that be?
oh, whoops.
I think that'd be for R.
That's R.
Yeah,
That's what I got for you.
Oh no, that'd be for I apologize. Yeah, that's for you.
You're at the first time. Or
No, it was just unit
Oh, the
wise.
units.
Yeah, unit wise. R would be the top. Yeah, I couldn't figure out how to do the second one because the table was, the units were different. It said times BTU and not divided by BTU.
I think that's just a typo in the table because somewhere else on that same table it actually shows like, the correct units.
Yeah. Yep, that was what I got.
Yeah, and then number 2 actually has you draw the numbers from the table. And this table is a little bit different from the one in the textbook, but I just use this one because I can, it has everything in one table rather than spread out over 5 or 6 pages is in the textbook. And the other problems similarly are applications. So like the I don't have my problem 4 on this one. This is problem 4. 2,900 foot retail space. Okay, what I would like to do is have you in class work on for classwork and is problem 2 and problem 4 on that handout. And so you want to work on that. And I'll have you submit your work before class is over, but this is good practice for the exam, especially problem 4. Problem 4 brings the psychometric chart in and ventilation calculation as well.
Yeah,
Huh?
I think number 4 said not to use the chart.
Does it say not
without
to?
using the second.
Oh, without using the chart. Oh, right, because this one is a heating one, so we don't have latent load to consider. And when you don't have to deal with latent loads, you can use the sensible heat formula. What QS equals 1.1 CFM delta T. So that one is yeah, that one you don't need the psychometric chart.
So Logan, your point is that there are values that are listed.
When was that?
Oh, in the table, it said they were multiplied.
Yeah, it's
Just that.
that's on
Okay.
So number 2 and number 4, and while you're doing that, I'm going to pass out some practice and review problems that you can do to entertain yourself over the weekend. Some people do crossword puzzles in their spare time. Other people do HVAC calculation. Thermo problems.
Thank you.
Yeah, soon. Yeah, all of my time has been right now heat transfer. That is amazing exam. I spent the whole day yesterday writing one exam. Like that's completely insane. I've never done that before. But it's because all I have for the past couple of years are online exams, and I need something for in class. And yeah, so in the next day or what, because I'm done now with heat transfer for a while, and now I can finish up those. I'm sorry about that. I'm just working at my physical limits and just a tough patch right now.
Is it better than online? Or is this the additional training?
No.
I don't see some of the
No,
things
because
in the table.
by the end of last year, by the end of our heat transfer class, I had everything online. And I could have just rerun that class, basically.
Gosh, so you got it all set up and now it's like you have to reset.
Exactly. That's what happened. And it's similar for this class as well. Trying to, this class is not as big of a change, but for some reason heat transfer just, a lot of things changed. This class would have been,
Yeah.
because I'm using a textbook, it would have taken a lot of work anyway.
I'm just trying to find out for some it doesn't
I
say
just wasn't
anything
happy with
paragraph.
my text last year. It's just hard to find it. I'm trying to find a proper way to organize this class and get the topics and write my notes up. Heat transfer, yeah, that's frustrating. Okay, so I handed out some practice problems, but those are problems. There's also concepts in this class, just like in thermo. And in some ways, I think the concepts are even harder here because you know, we're always doing the math side, but when you stop and think about moist air and how it behaves, and you try to explain in words, you know, what happens when I take a chunk of this air and I cool it? Well, I can cool it at constant temperature, I can cool it at constant pressure. What happens to the relative humidity when I cool it at constant pressure? What happens to the relative humidity when I cool it at constant temperature? And these are things that we don't often think about if we're just doing the design calculations. So the concept questions are more thinking about conceptually what's going on in the refrigeration cycle, what's going on in the air conditioner. How would we describe it to somebody that isn't an engineer? And so that's what the concept questions are. So there's some multiple choices up here on the front, and then there's just some kind of thought questions on the back. And you should be able to find the answers to these in my notes, or maybe the combination of my notes and the reading.
I guess we just have to pick some from the table. This says it's 15%.
Cool.
It's 15%.
I mean, yeah, there are actually tables that have kind of all five components.
I kind of figured it was the idea,
Yeah.
it's the lowest value for one and four of gold.
Yeah, use the, yes.
I think it's a question that you might know. We have a three-quarter engineer guy, so we get the data for the
Yeah, that's fine. Use the low end or the midpoint. Low end is kind of efficient.
There's nothing on the wind speed or the interior, or the interior and exterior values, or assume a 7.5 on our wind.
Did you do this? I did, yeah. I still have 3 more problems to figure out. Did you? Okay, yeah. Good luck.
Yeah, you can just state what you're using, what your assumptions are. Yeah, it's not.
I have to figure it out. I'm gonna try and work on it later today because I've done it 3 times, so I'm gonna try and just figure out how to do the other problems. They're unusual. I don't want to spoil it because I want, but it's some of them are unusual. Yeah, I know it was weird. I thought it was static. So I'm like, this should make sense. I don't know. I'm not good at looking at a problem and knowing how to fix it immediately. That's the problem I have. It's not like I don't know how to do it. It's just I need to do it.
Yeah, at first, I didn't know.
And where does some patterns and stuff like that? thought, huh, do I need the density? And I looked in the textbook, and in the textbook, if you look at table 5-5, it actually says aluminum sheathing, foil backed, and then it already says it's 3/8 of an inch in the table.
Oh, so this value is redundant if I do this?
Yeah, there was no reason to do. There was no reason to change it.
So that's probably
Which
what
is
my
the
error
thing. Yeah, that
is.
was what I
So
was
you just leave it as 2 points.
Yeah, which was what was confusing to me because I thought, oh, I need to do something too. And then I looked at the table because it said that he had gotten it from that table in the
Oh,
text.
that's-
And when I looked in the text, it actually said aluminum sheathing, foil backed, and then it said 3/8 inch.
Okay, thank you. That's my
Yeah.
error, for sure. Thank you. Okay.
So we are finding the R value for each one, each material,
Yeah,
and you add them together, right?
yeah, that's how you get the U value, and then you have to do it for multiple configurations.
Okay. Gypsum board. Do you have gypsum board here?
Yeah.
Oh, yeah. So, this is that.
Yeah, you just read it off. Yep.
The second one, which is your flow part.
For gypsum board? Yeah. Yep. Yeah. I'm still trying to solve for the. Excuse me. I'm still trying to solve for the. I just solved for the step part, but I need to solve for. That's a bummer. I just messed up on these steps.
Well, yeah, so you put it, you have to still submit it to the form.
You said just take the lower one for the. Yeah, so I took the. I just looked, or no, I just did the 5.5 and 20. I just took the lower value. That's a bummer. So I'll just take that and then minus.
Yes, so just have to take the.
Which one?
And I put in for this.
That's okay. I wasn't thinking about the stack. What?
The fiberglass.
Made a mistake, so I need to fix this. What did I just do there? That's not happening.
So, you could ask, are you good? Like, I tried to net this yesterday and I was confused by that, when it says like 15%, you know, 85%. Oh shit. Yeah, that only accounts for like this part and not the other bits or like. Oh, okay, so I was like, where's the take like this total value?
That's okay. Shouldn't be as bad.
Yes.
Why do you assume that the outside surface is 7.5 on the aisle anyway?
I just made that assumption. I could have chosen either one because it wasn't specified whether to do it for winter or summer. If it's a summer design, we would use 7.5, and then if it's winter, 15. But there isn't really anything in here to tell me which one. So you could choose either one.
Yeah, I actually really like that. I got through it.
I use just the straight 19 because I think those are for if you are not. We do the interior and exterior. Air.
It's in the back.
Used our 1.2 average lunch.
Can I get a copy of the concept question?
Oh, yeah. And you got the other ones?
Yeah, I guess I have the other one.
Wait, are we supposed to have the inside and outside surface as well?
Yeah.
Oh, for,
Yeah, both. What? Fire store.
oh, first,
Because I was looking at this as 50.8 to 0.2.
Yes, that's-
So one is more on there.
yeah, hold on, I'm just gonna wait for this.
See, I would just.
see one.
I, for some reason, ended up using the did not
Yes, sir. Yes.
So I see that he's doing that. So it's like he's still like yeah, it's still pretty low.
And the units of R should be hour feet squared degree F over BTU. Like that table has a little misprint there. It doesn't have the little slash there, just a dot.
I don't know why I thought it was like other agents. One of the other ones. And FOP.
Well, all the universal items, he's got GS plates on that. So there's a half a job.
Does it look like what you got?
All those had to be.
Close. Huh?
Oh,
No, just add everything up. This, but then this replaces the insulation. And then this back to here.
Did you say that again?
Oh, the stud replaces the insulation.
Okay.
So in the studded part of the wall, so it looks like. So it looks like that. So the studded part of the wall is that part, and then this is the stud wall.
It's always A. Literally all numbers. It's pretty safe guess. Yes.
This case, we have to go like, the 6 inches. Yeah. Too late to change now. 6 plus 7. And so between first and fiberglass, that's where the percentage comes in. Correct? Like between the insulation and the first and the out, that is where the percentage comes in, right? Just for that section. Oh, yeah.
It's just part of the wall is that, and then the studded wall is everything except fiberglass with stud. Yeah.
Oh, Dr. Collins?
Yeah,
Are we supposed to skip over number 3?
yeah, we're just gonna, yeah,
Okay,
these 4 is more of a,
okay.
takes us back to connecting the lights with the second line.
Okay. Okay.
Yeah, so I just.
You still want us to solve number 3, correct?
Yeah, but,
Okay.
yeah. I'm
Outside
just
of
gonna
class,
ask you to
okay.
turn it into-
13% times.
Oh, okay.
Yes, plus the 85% times the R value. Would that be, I mean, right? Okay, that's what it's making.
We still start.
I kind of looked at them as,
So I want to make sure everyone understands how this is set up. That when we have the structural part of the wall, we're dividing the wall into the structural part and the insulated part. They're essentially the same wall, so they have the same inside and outside layers. It's just that the insulated wall has a hollow space between the structural members. So this is like we're looking down on the wall. This is inside the building and the outside of the building. And if it's warm inside, cold outside, the heat flow is going to be down. And most of the wall is, is insulated, and so that insulation is a key layer. And so in this part of we call this the insulated wall. It represents
you know, this part that has the insulation and the hollow place between the studs. So it has all of the layers in front of and on the other side. But then when we get to the stud, so we move from here to here, everything on the inner part of the wall and the outer part of the wall is still the same. So it's still the same up here and down here. But the middle part, we replace the insulation with the stud, or the structural member. So we need the R value of the structural member there. Okay? Does that make sense? And then typically these studs are 16 inches apart from center to center. And then this hollow section here is filled with insulation. Fiberglass bat or blown in, but it's a hollow space between the structural members. And then this section just repeats. See, in heat transfer class, we would have called this a set of resistances in parallel. Right? Remember how we handle parallel is you remember doing that? And yeah, that's another way to do that. That's another way to determine the equivalent resistance when you have different materials in parallel. It's just like parallel resistors. Remember resistor networks, and the resistors were in parallel, and you had to do this calculate the equivalent resistance. This is actually, to me, it's an easier method where you just divide the wall into sections based on the fractional amounts. Some fraction is going to be insulated, some fraction is stud, and then you just take the weighted area and sum them up, and that way you don't have to do this complicated 1/over stuff. I've never even seen this done in HVAC.
You multiply, because it's 1.25 per inch, and there's 5.5 inches.
Oh, okay.
Because a 2x6 is a 1.5 by 5.5.
Oh, that's point. I thought it's minus or something.
Anybody have any numbers for the U value for the insulated and stud part?
For insulated, I got 0.0441.
0.044?
Yeah, 44. And then for the stud, I got 0.095.
What was that?
0.095
Those are our values.
for the stud part. Not for sure if that's what other people got. That's what I got.
Oh, this series says R over U. I didn't use any of these,
So then your U overall,
Was 0.0517.
What was it?
0.0517.
So think back in the days before there were computers, widespread computers, and you had to do this by hand. Every material in the wall, and the floor, and the ceiling, you had to look up individual R values and do all this summation, and it's just pages and pages and pages of calculations. Yes, sir.
I did want to ask in general before the software came along in terms of having those databases, would you have to look at manufacturer specific catalogs for R values, or was there a like reference book that was published of R values?
Yeah, they're pretty much all in the ASHRAE handbooks. There's just an immense amount of, and those have been published for decades, and they're updated every 4 years. And yeah, so that's where we find pretty much all of it is standardized. And now with the structurally integrated panels and modular construction, building assemblies come pre-made, and so they already have a U value. So that it's a lot easier to do engineering design when you can buy composite assemblies and just put them together like Lego blocks, as opposed to having to build a wall layer by layer on the site.
Thank you.
Curious, I don't know if I missed this, but what made you choose the Explorer 7.5?
Yeah, I just, it didn't say.
Yeah, of course. Oh no, don't worry.
Normally it would specify, but when you do your analysis, you say, okay, we have this design, but it doesn't.
But yeah, you're not halfway through the year or okay.
It's really the only number that.
And I think I read, like you take the two, those are taking like the extremes, right? Like say like the coldest day of the winter and the hottest day of the summer.
Yeah.
That makes sense.
And we would have to do it for the roof as well, and the value for the roof would depend on whether it's got
Yeah. I can see that in lots of them.
everything the roof.
Yeah, that's it. All three, the roof.
Because roofs are pretty standard, generally we can look up just the U value for a standard roof.
So how did you get the overall 0.8?
Which part?
The overall, which is 0.85?
Yeah, or 0.8, or, oh, that's in the problem description. So the problem description says 85% of the wall is insulated and 15% is stud. So it's a weighted average, so you're finding out what the heat transfer coefficient for the stud area is versus the insulation area, and then you're taking those and then averaging them over the area, because essentially 85% of the area is insulation, 15% is structural membrane, if that makes sense.
Yeah.
Yeah. Yep, happy to help.
Okay, I got, yeah, you guys can do that. Here for Steve.
Yeah.
Well, I took it to the other side, I got the same R values for the inflation as that, multiplied by the percent for each of them, and then add them. That doesn't work. What's this? That's 50% of. Yeah, that's 50% of this. Oh, you left it up for Oh, okay.
Anything I can do to help? Or? Oh, Dr. Carnes?
Got paper
I should have used that.
It's nice.
Okay, on the fourth problem 4 is using the ventilation calculation that ASHRAE requires by its standard, and which codes require as well. And that says that the ventilation air is going to be equal to a contribution per person, how many people are in the space, plus a contribution from the area, how big the space is. And these numbers for RP and RA, that depends on the purpose of the building. So you have to look it up. If it's a retail space, as it is in this problem, there's a number for retail space. If it's a bowling alley, a gym, swimming pool, that's going to differ. The number of people, the client might say, my building's intended for X number of people. So in this case, the client says, I envision 40 people in the space. More often, you won't know that. You're not going to have a number from the client. And so you go to what ASHRAE recommends for each, depending on the purpose of the building, is they'll have a certain number of people per 1,000 square feet. And then you multiply that by the number of square feet. And in this case, we get 43.5 people. You won't round up, we don't have half people. Except maybe for me, I feel like a half a person. Half of my brain and my physical and mental strength have dissipated. I gotta take some time off to build it back up. So this is 44. ASHRAE says 44 for a retail space. The client says I want 40. I envision 40. And when you have that conflict, you go with the higher number. Now, why go with the higher number? Because this is going to give you more ventilation. You want to err on the side of too much ventilation rather than too little. Okay, so if you're ventilating for 44 people and there's only 40 or 30 or 20 people, you're going to be covered. And especially now, the trend is more ventilation. The current ASHRAE magazine just has something out on not only more ventilation, but also now applying greater filtration and purification systems to try to cut down on the spread of infection. There's actually an equation you can use to figure out the risk of an infection being transmitted in a room when you're given certain characteristics about the space and the number of people in it and the ventilation and things like that. And there's a rule of thumb, I forget what it is, but every time, with each certain increase in the ventilation, you reduce the chances of infection being spread by some amount. It's significant. I can't remember what it is off the top of my head. Ventilation, that is really the way to go to cut down. Every increase in ventilation reduces the chance of infection spreading. And it's probably why airplanes are thought to be relatively safe, because they have high ventilation. The air in the cabin exchanges like 5 times an hour, which is much higher than it is in most ordinary buildings. So we find out number of people that is a recommended number for the space, and it's 44 in this case, and so we're going to go with that number. So 44 people, and our area is 2,900 square feet. And then, we look in the table for these values of the air rate. RP is the air rate per person. And for retail space, it's table 6.1, minimum ventilation rates in the breathing zone. Okay, retail sales. Got a barber shop. Anybody up for designing a barber shop? Beauty and nail salons, coin-operated laundries, mall common areas, pet shops, and a supermarket. And then there's just general sales, and that's the number we use, general sales at 7.5. And that's given in the problem statement, but we can look it up. So it's 7.5. That's CFM per person times 44 people, and that's our person component, and then our area component. The table tells us that our area rate is 0.12 per square foot. 0.12 per square foot. Okay, so we run this out, 7.5 times 44 plus 0.12 times 2,900 CFM per square foot. We get 678 CFM, right? So if I'm designing the HVAC system for this space, what I have to think about now is I'm going to need outdoor air. .678 CFM with outdoor air, and that's going to mix my exhaust. I didn't draw that. I didn't draw that properly. That should be. So now my design is going to key off of what my ventilation air, my outdoor air has to be. My supply air flow rate will be determined by the space load. And then I can calculate my mixed state from that, based on that information. This should be maybe 25% of the total mixed air, 25 to 45% of the total air going into the conditioning unit and into the space. In some cases, it might even be 100% dedicated outdoor air system. Okay, so 678.
Where did you get the 15, what chart are you looking at for 15, or 1,000 feet? Like, what part of it is that? Is it in the front? Or back?
Yeah, it's given in the problem, but it's, you can find it on page 257 is the table, the complete ventilation table. 257.
I did want to ask for part B, do we need to know any of the properties of the return air? Because I was thinking in this case, the mass flow rate would be conserved, so if we knew the specific volume of the outdoor air, we could get a mass flow rate. But I don't know if that,
Yeah, this is a situation
just because
where.
we're not using the chart.
Yeah, since you're not using the chart and we're not, we don't have any rate, we're not changing the moisture in the air.
It'd be a QS, right?
Yeah, we can use the quick and dirty.
QS is 1.1, okay. Okay. And then it'd be the temperature difference, correct? Okay. Okay, thank you.
Yeah. Yes.
So for that equation, the return air, wouldn't that be the mixed air going into the heater, right? So the return air.
Oh,
is
no,
that
because
there?
this is the heat load on the space. This is the energy balance on the space here. If you're doing the energy balance on the conditioner, yeah, you use the mixed air. So when you're calculating the cooling load, calculating the cooling load and the amount of moisture you're taking out of the air, you would use the mixed air.
Okay. That makes
Yeah.
sense.
See, this QS is the sensible load on the space, and then we have the latent load, but we can ignore the latent load in the wintertime. We're not really concerned about that. And this is a wintertime. This is a wintertime calculation here because we're heating the space.
First of all.
Yes, sir.
Can you remind me again why we can ignore late load? Sorry.
While
Why
what?
we can ignore the late load?
Because when we're heating the we're adding energy to the air, and latent load adds energy to the air, so it's moving in the direction that we want to go in. So it's helping us rather than hurting us
Okay.
in the wintertime. Usually, there's some situations, and really when you get into larger buildings and more sophisticated systems, we do want to track, we want to monitor the moisture because normally we have to humidify the air in the wintertime. Okay? So the latent load is usually something we want because A, we want to put energy into the air to heat it, and B, heating it is going to dry it out. And so adding moisture to it helps to improve the comfort of the air. So in the wintertime, the latent load usually doesn't work against us. Okay? However, in a more sophisticated system, you probably will want to humidify the air. We want to control the moisture by adding moisture to the air, not taking moisture out. And in that case, we would have a humidification system working alongside the heating point. So if there, you might heat the air, and then there'll be little nozzles, little spray nozzles that spray steam or hot water to just add some moisture to bring the humidity out. Yeah.
That's the word, all that, is that part of the weight load? Do we have to
it's not latent load, it's latent energy that we're adding to the air. Well, the latent load is the, comes from the people and the stuff in the space that's adding energy to the space.
So would we need to calculate QL in this case?
No,
No, you would just take QS to be the, okay.
yeah, because we're only heating sensibly, and so all of our calculations.
We're not worrying about any of, like you're saying, the additional, water vapor that'd be coming from people in the building.
Right, yeah.
And so in that case, and I think you mentioned this earlier, that would actually be helping.
Yes.
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 Okay, thank you.
Yeah, you might think we'd wanna subtract it. because-
Yeah, it's kind of counterintuitive to think of that, but it actually helps.
Yeah, but we just ignore it because it's helping us.
Mhm. Thank you. Okay,
We all,
so I need to find it out. Make separate parts.
yeah,
Yeah, but they're.
yes.
That's what I couldn't figure out. So.
Sensible load.
So then we know the return air 69 degrees in the problem. Because we see that the space of heat remains at 69 degrees, so then that would make that the return air.
Yes.
That's good. Okay, so we know TR.
Like, I
Yes.
guess with, like.
Yeah, so then what would TS be?
Well, they said it's 20 degrees above
Right.
the return.
Right.
So we know TRTS and
Yeah.
QS are based on, I mean, well, little QS.
That's where.
So we're just solving
see what I'm
the
saying?
The big QS.
Okay.
Yeah.
Right, so your unknown here is big QS. That's the flow rated supply air.
So the return is the return's the 69, correct? Oh, and the return's
Yes,
89?
yeah,
The return's 89?
no.
Okay, thank you. Or did that one use 13 for some reason? Which doesn't make sense, 'cause that would be October. So a lot of CFM for the supply.
That's amazing how big these are.
Yeah.
Systems can be. Yes.
No, it's just because you have a huge
Best
armor.
used.
Yes, but oh, you know,
I drew this in the summer. Actually, this is, this Q is leaving because it's winter time. I'm just so used to doing summer calculations that,
So it'd be negative, right?
yeah, so it's really negative. QS would be negative, and that's why it would be positive, right?
Can the flow rate be negative now? Oh, well, yeah, you're talking, okay, sorry, you're talking about.
Yeah.
Yeah, but that's.
No, it's Yes.
Oh, no, 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 it isn't.
Oh, yeah, it's an energy balance on the space.
So it isn't CFM. The book has.
The big QS is volume.
I just look at that and go, where's the unit?
CFM.
Oh, yeah, okay.
So this is the formula that HVAC engineers always use, that it has unit conversion built into it. That's where the 1.1 comes from. But if you wrote this out formally, we did the formal energy balance on the space, we would have supply air going in at, you'd have the mass flow rate of the supply air times its enthalpy. That's going in, and then it has to equal what's going out, which is the heat that's leaving, that's transferring outside because it's cold outside. That's QS, and then the return air, which is MR, HR. So if we solve for QS, then QS is MSHS minus MR HR, right? Well, by conservation of mass, MS equals MR. Yeah. So QS equals and since we're only dealing with the sensible part of the air in heating, we can replace the delta S with delta H with CP delta T, so QS equals, and the mass flow rate is equivalent to the volume flow rate divided by the specific volume. And then CP, and then TS minus TR, right? So that would be our formal energy balance on the space. And then CP of air is 0.24. And there's an assumption being made here that the density of the air is just the density at standard conditions, which is 0.075 pounds per cubic feet. So if you make that assumption, density is 0.075 pounds per cubic feet. CP is 0.24 for air. Then this equation takes this form. And so everybody uses this, but it originates by doing the formal energy balance on the space. But if we were using SI units, you wouldn't use this because this only works for English units. It's designed to take English units in CFM for big QS, in degrees Fahrenheit here, and then you'll get BTU per hour here. So you want to go back and review those notes where I developed these equations. There's one for QS.
There's one for QL.
There's one for QL, and then you add them up to get Q total. Those are kind of quick and dirty calculations. I don't like to use them because our air is often not at standard conditions. This is assuming the air is 68 degrees. Well, the air is, it's going to be okay for the return air condition, but at 89 degrees, the density is going to be quite a bit less than 0.075. So I like when I can to use mass flow rate rather than volume flow rate, but sometimes you don't have all the information. We would need the psychrometric data so that we can look up specific volume if we were going to calculate the mass flow rate, but I don't have that information. So I'm just going to assume that the volume flow rate at standard conditions, that's going to have to be good enough for me. And I'm going to be assuming here that there's conservation of volume flow rather than mass flow. And again, that's an assumption. That's an approximation that is going to have some error in it, but sometimes that's all we can do. We don't have enough information. We have to do what we can. So in this analysis, because I don't know specific volume, I'm going to have to assume that QM equals QR plus QS. I'm sorry, QR plus QOA. We already determined that our QRA is 678 CFM. We solved for, we calculated our supply flow rate here. What did you get for that? Yeah, 5,900 and something. 910. So, yeah. So I come back up here, and I say, oh, okay, I'm taking 678 CFM of outdoor air, and I have 5,910 of supply air. Well, that's going to tell me what my return air has to be. So, I'm sorry, what my mixed air has to be. The mixed air is equal to the supply air. So supply air. Does that make sense?
And then you could just take the fractions of the flow rate, correct, and then figure out the temperature from that?
Yes.
So if you know that 5,232 divided by 5,910 is at 69 degrees, that makes sense? Is that how that would work?
Yes.
Okay.
And
Thank
you get your mixed air temperature.
Yes.
Yeah. Yes. Yes. Yeah. Yes, I don't have any conversions because it's already built in.
Even though the little QS we put in is BTU per hour,
Yeah, it already builds in the dividing by 60 or multiplying by 60. Yeah.
Trying to find the return.
Return temperature is
It's actually marked.
The floating, yeah,
Yes, sir. Yeah, we don't even have to use futures. It's automatic. We just use this formula. Yeah.
So the 1.1.
It's a conversion. Yeah, it just makes it work. Yeah. This is the thing with HVAC is we do things that just go against how we teach the students to do engineering calculation, right? It's just because you're in the field, you're doing things fast.
I know how to do anything you want.
You don't bother with unit conversions. You know, things
Oh, I know.
formally.
I know exactly.
Okay.
Did you get a seat? Did you get There's an equation for mixed temperature. Wait, are we talking about C now? There's an equation for temperature of mixed air. It's on note 3. And I got a number. No, it's pretty warm. No, I don't think it's ready to. I got it. You're probably right. For sure. Probably right. I just But if I do it the other way, I'm gonna get 20 degrees.
When you do fifty,
What's the next word, right?
yeah, I'm trying to figure out how to use the ratio of the
Ratio of the flow rates. But I don't know how that works.
Okay, 2021. That's what you did.
Oh.
Okay, next day, right?
But doesn't that require properties we don't have? Okay. Well, I don't know, I was just wondering.
It doesn't.
I mean, okay, here's what I did.
So that's in terms of mass. That's in terms of mass.
Right, so I just did mass flow rates. I figured they.
But I think we only have volumetric flow rate.
Yeah. Yeah.
I'll just wait.
You want to know the name?
Oh, was that for both of us?
Yeah.
Oh, okay. Okay. I can write down for the second. Oh, okay. That's fine.
Switch roll.
Oh, it's supposed to be in tons.
I haven't done the third.
Okay, here are the answers to those problems. You wanna
Oh no, I did do that.
continue? 62.6. So can I collect your answers or your work, or whatever you want to turn in to me to document your work? And we do have our exam on Monday. You got lots of practice problems to work, and I will post solutions in time. It's going to take me a little while because I've gotten so behind on things, but I'll be working on these just like you. And yeah.
Sure. Ask you a question.
Yes, sir.
Is this?
Okay.
So I was basically
Say thank you, Pfizer.
find the total surface area of the walls. And then multiply that by the brick. See which one you're doing now.
Yeah.
Is it, so this is split, it's like the outside temperature minus inside, right?
Yes.
Okay, and then times 85%. So I was just curious, because that would give me a negative answer.
Well, yeah, probably it's easier to do the U, calculate the U first, the overall U. And then you just have that U times the total square footage.
Thank you, sir.
Okay.
And whether it's positive or negative, it doesn't really matter. Generally in HVAC, we assign positive. And but we just have to make sure that we have correction. So if it's a positive number, we have to specify inside to outside, or outside to inside. But if if we're designing for winter conditions, it'll be understood. Even if we don't specify it, the numbers are all positive, it's going to be understood that the flow is from inside to outside. Yeah, the exam will have the form of, do you remember this? Well, so you all had the online version of my classes, so you haven't really seen what my own class exams look like. But there's generally, part one is concept questions that are usually multiple choice, and that might be 20%, 25%.
We did have that. I remember that online where you had the concept questions first
Yeah.
and you had the workout problems after.
Yeah, workout problems would be 70 to 80% of the exam, like 20 points per question or something like that. Yeah.
Maybe sign it, so it doesn't matter.
Yeah, me too.